Hi everyone, this is Solid Gloria Molecular Thermodynamics lecture, Chapter 1, Energy Levels of Atoms and Molecules. This is the second part, Module B, Translational and Electronic Energy Levels. Let's calculate them from quantum mechanical viewpoint. So translational energy, we utilize particle in a box model. So in one dimension, it is described by this model. So inside of the box, we set the potential energy B equals 0. Outside the box, the potential energy is infinity. So potential energy is infinity, so particle is confined within the box, but the dimension is x, so particle moves from x equals 0 to x equals a only. So in this case, the Schrödinger equation, the V is given in such a way that outside x equal less than 0, x greater than a, 0, only between 0, x and a, the potential energy is given V equals 0. So then that's what it is. So in the region a and 1 and 3, there is no particle, meaning is psi of x equals 0. So the partition, the particle, the wave function, state function must be continuous. So when x equals 0, when x equals a, then must be 0. And this is what we call the boundary condition. So in region B, region 2, we only solve in region 2, which is we call 0 region, and then the Schrödinger equation is reduced in this simpler form. And notice that there is no potential, and this is only kinetic part only. And then what you see here is that what you make a derive twice, you will get you derive twice. See, let me clear this. You derive twice of some function. You get the sum function times energy of constant in this case. So that kind of behavior you can obtain from sine function, cosine function, or exponential function, complex exponential function. So what we choose here is the psi x, a cosine kx, and b sine kx. And of course, that k has this relationship with to the energy. Okay, that's how we solve it. Well, we have done this in quantum part, so I will just briefly describe it and shift over, right? That's okay, yeah. So with the boundary condition, and then this is a kind of trial solution. So that must meet with that boundary condition. So psi equal psi of 0, which is this is 0, and then this is 1. So which is a is 0. And psi of a, b sine ka equals 0 only when this ka is integer multiple of pi, n equal 1, 2, 3, like that. So now what we get is the energy was written in terms of k, then that is reduced into this energy. En is h square n square over 8ma square. In this case, there is a number n, so we index that energy with n. That n is the quantum number in this case. And then, given the quantum number, also the wave function, given the energy, we obtain a wave function. So wave function also contains the index by the quantum number. So psi n of x is b sine kx, which is b sine n pi x over a, and is the quantum number. So this is the actually the size absolute value square summed up or integrated into one, meaning is normalized. So normalization condition will give you what the value of b. So b is square root of 2 over a. So wave function psi n is square root of 2 over a sine n pi x over a in this inside of the box, of course. So what we have here is the energy and wave function corresponding to the quantum number n equals 1, 2, 3 to the infinity. So this is the important or result that we need to obtain translational partition function. Yeah. So that was one dimension. And in reality, particle moves in a box, three-dimensional box. So we need to expand that dimension to include y and z. So in that case, we do minus h bar square over 2m here, and x, y, and z derivative, which corresponds to px square, py square, pg square, right? So that's what it is. And then which is equal to energy times the wave function. And then the dimension of the box is x dimension is 0 to a, y 0 to b, z 0 to c. Okay, so that's the boundary, and then that must fulfill the boundary condition. And then this is three-dimensional Laplacian operator, so del square. Okay, so minus h bar square over 2m del square psi equal e psi is the Schrödinger equation of this particle in three-dimensional box. And then it's solved. Well, x is the 1D particle in the box problem, the same as, and all large X, capital Y, capital Z has the same form of square root of 2 over dimension A, B, C, and sine n pi x, y, z over ABC, you know. And so that's what it is. So then actual total psi is a multiple of product of x and y and z. Well, anyhow, I just mentioned the solution, but how we obtain the solution is that because this is the partial differential equation, so we must make a separation of variables, and then variables are separated by capital X, capital Y, capital Z, and then we plug into psi here, and then these are all decomposed, and then we make this energy as Ex, Ey, Ez decomposition, and each is corresponding to that, so that we separate the variable. So each separation, that separation yields us three one-dimensional box problem, but the dimension itself is given A, B, and C, and then each has different set of quantum numbers in X dimension, Y dimension, and Z dimension. But our wave function is a product of this large X, large Y, large Z, which is 8 over ABC square root, and then sine, and x pi x over a, sine, and y pi y b, sine, and z pi z over c, like this. So this is it. And then energy is h square over 8m, and then nx over a squared, and y over b squared, and z over c squared, like this. So energy and wave function are obtained by solving three-dimensional three-dimensional particle in a box problem. So if that box is cubic, A equals B equals C, then this is reduced in this form. H square over 8ma square, A are the same, and then nx square plus ny square and z square, kind of square of quantum numbers, sum of square of quantum numbers. Yeah. So in this way, we obtain particle in three-dimensional box, which is like you have a gas and then gas molecules in some container, which could be a box, and then we obtain the energy of the translational energy of the molecule. Now we do electronic part, electronic energy. Well, we haven't done vibrational part yet, but we have done it in quantum chemistry part. So electronic potential surface, which has a vibrational degree of freedom, and then the zero of energy, the lowest energy of that total system, is not electronic ground, but electronic ground. Above the electronic ground, the 0 point energy is there. 0 point is 1/2 of the vibrational energy. So 1/2 of the vibrational energy is the 0 point energy, so-called GP, 0 point energy, GP energy. If that shows up in a vibrational spectroscopy, we call GPL, 0 point line, or just like that. I know, 0 point energy, I would call it here. And then this is 0 point energy level, and that's actually the electronic equilibration. So this part is so-called bond length, or anyhow that distance between two atoms. Okay, and then that's RE, and that energy is dissociation energy. Dissociation, and if that's a diatomic molecule, then that's dissociation energy into the infinity. Okay, it's infinity. So 0 point energy is added to dE, gives you d0. Then dE is d0 plus 0 point energy, h nu over 2. So this is the lowest electronic energy, or lowest electronic energy state, which is the ground state. Anything above it are all are excited. If this is the first one, and that is first excited states, like that. The claim here is that the distance, the excited state energy is so large, so don't need to be counted, because you see the exponential term of this excited state energy is over kT. That is so large, then this is so small, so we don't need to count. We only count the ground state energy, which is maybe the reference level is 0 here, and then probably we need to count dE here. Okay, that's the only one. Okay? That's what it is for the electronic energy. And electronic energy is concerned, we can calculate for hydrogen atom. So which is the H psi equal E psi for the hydrogen atom is minus h square over 2, I would say the reduced mass of the electron and the hydrogen atom, and I just use del square. And then the potential energy 4 pi epsilon 0 r over, if that's just a normal hydrogen atom, which is G is 1, but I will just use G E square. and that's H psi, you have E psi. This could be solved analytically. You have to solve associated Legendre equation, associated Laguerre equation. We have done it in mathematics for physical chemistry. And then you can obtain energy and the wave function. We call that orbitals, 1s orbital, 2s orbital, just like that. And in case of the molecule, even H2 hydrogen molecule, you cannot do it analytically, but you can use digital computer to solve this equation. So even we can do, like, let's say maybe 1,000 atom molecule nowadays. Yeah, that can be done. So we can obtain molecular energy by doing Hartree-Fock calculation, or beyond Hartree-Fock calculation, we obtain molecular energy. And then utilize translational energy to get translational partition function, and then electronic energy to get electronic partition function. Nonetheless, well, we can do calculating molecular energy in quantum chemistry package or programs. Instead, what we can do is utilize some table. They publish table. They collect all kind of molecular data and made a tabulation. This is an example of diatomic molecules utilizing rigid rotor, harmonic oscillator. Those two will be dealt with in part C and part D of this first lecture, lecture for the first chapter. Rigid rotor, harmonic oscillator. I use the market rigid rotor and harmonic oscillator approximation. And molecule He2, yeah, D2, H35Cl, HBr, HI, Cl2, Br2, I2, O2, N2, CO, NO, Na2, K2, like, well, for example, these molecules, fundamental vibrational wave number, and rotational constant, and then equilibrium bond length. And degeneracy means that electronic energy level, the degeneracy of the electronic energy level, most of them are singlet, and oxygen, as you know, of triplet, and NO is doublet, and all others are singlet. And then dissociation energy given in kilojoule per mole. So utilize these numbers for the ground electronic state. Then we can calculate the electronic partition function of the molecule. So that's how we do for translational and electronic energy, then obtain molecular electronic partition functions. This is the end of the second part of the chapter 1. Thank you for listening, and there are 2 more to go. So let's do it. Let's do our